Hello everyone, welcome back to my video. In this video, I will show you two examples. One involving reinforced concrete beam, and the second example is involving the stress concentration. Alright, so example 4. So let me read the question first. The concrete floor slab is reinforced with 16 mm diameter of steel rod. The modulus of elasticity is 200 GPa for steel and 25 GPa for concrete. With an applied bending moment of 4.5 kN for 0.3 width of slab, determine the maximum stress in the concrete and steel. Alright, so based on the question, okay, so what we have to do is to determine what is the maximum stress, okay, maximum stress in concrete, okay, concrete, and also the maximum stress in steel, okay, in steel. So given the diameter of steel rod, so the diameter of steel rod, okay, is equal to 16 mm. Okay, and then what else? We have the question also give us the information about the E for steel, which is equal to 200 GPa, and E for concrete is 25 GPa. Okay, and then the bending moment is applied on the concrete beam, okay, with the value of 25 GPa, okay, for the width of 0.3 meter. So we will analyze the beam for 0.3 meter only. Okay, so we analyze from here to here. Okay, alright, so let me draw the reinforced concrete beam first. So that is the concrete beam, and then we have steel rod, okay, and the distance here is 0.15 meter, and also from here to here is 0.15 meter. Okay, so basically there are two steel rod involved. This is the half of the diameter. This is the full diameter of concrete. Okay, and then there is another half diameter of this is a full diameter of steel rod, and this is another half diameter of steel rod. Alright, okay, now let's start with calculating the transformation factor N, okay, which is N is equal to E steel over E concrete. Okay, is steel over E concrete, so means that we will transform steel into concrete. Okay, we transform steel into concrete. So the N is equal to 200 over 25, and using calculator we get 8. Okay. Alright, so sigma max, okay, for the steel basically is given by sigma max is equal to MC over I, but for steel sigma max is equal to MC over I multiplied by N, because we will transform steel into concrete. Okay, so now from this equation, from the flexural equation, what we have to calculate is the I. Okay, we need the value of I in order to calculate the stress, and in order to calculate the I, okay, we have to know where is the location of neutral axis. Okay, we have to know where is the location of neutral axis. After that, we can calculate the value of I, the moment of inertia. Alright, so as I said, the concrete, okay, is strong in compression. Okay, but the concrete is weak in tension. Okay, so when we analyze the reinforced concrete beam, what we have to do is we will remove the concrete, okay, the part of the concrete below the neutral axis, okay, neutral axis, and so that we assume all the tension force or tension stress will be carried or will be supported by the steel rod, okay, the steel rod. Okay, now let's we draw the concrete beam, okay, the concrete beam without by removing the compression, the tension part. Okay, so that is the beam. Okay, so we assume this is the neutral axis. Okay, this is the neutral axis. Okay, so for the beam, okay, the concrete beam, the concrete above the neutral axis will remain. Okay, but for the concrete below the neutral axis, we will remove from the analysis. Okay, so we will assume that beam cannot support the tension load. Okay, tensile load. Okay, now okay, so that is the material for the steel. Okay, transform to concrete. Okay, because we transform into concrete, so instead of area, so we have to multiply by n. Okay, so the area for the concrete that has been transformed into concrete is given by NAS. Okay, you can see how to do the transformation from the previous video. Alright, so now we assume here is the x. Okay, the distance here is x because we don't know exactly where is the location of neutral axis. So we assume the neutral axis is actually is if we measure from the top to the neutral axis, we assume the distance is x. Okay, and then here is 0.3, so width of the concrete beam. And then of course the centroid for the overall concrete will be at the line of neutral axis. Okay, and then based on the equation, we know that here will be equal to here from the top surface to the steel rod, okay, is equal to 0.1 meter, so that the distance from the neutral axis to the steel rod, okay, steel rod is equal to 0.1 minus x, okay, minus x. Alright, so from here we can determine the value of x. Okay, from this illustration we can calculate the x so that we know the location of neutral axis. Alright, so first, before we calculate what is the value of x, let's determine what is the NAS. Okay, so the area for the steel is given by pi over 4 d steel power of 2, okay, multiplied by 2. Okay, so this is because we have a 2 rod. Okay, so for the distance 0.3 meter, we have a 3 rod. Okay, let's go back to the previous slide. So we have half of the rod, okay, one full rod, and half of the rod. So the total steel rod is equal to 2. So that's why we multiply by the 2. So here is equal to pi over 4. Okay, the diameter is 0.016. Okay, square multiply by 2. So we have here is 4.021 times 10 minus 4. So that is the meter power 4. So therefore, the NAS is equal to 4.021 times 10 minus 4 times 8. So equal to 3.217 times 10 minus 3 m power of 4. Okay. So now we can apply in order to calculate the X. So now we determine, okay, let's say I put here, we determine X. Okay, so by using the summation of YA is equal to 0. Okay, so where this equation come from? Okay, you can refer from the previous video. Okay, please refer to previous video. Okay. Alright, so now, okay, let's expand this equation. So equal to YA. Okay, so for part 1 plus YA for part 2 is equal to 0. Okay, or shape 1 or shape 2. Okay, part 1, part 2, or shape 1, shape 2. So this is the shape 1, this is the shape 2. Okay, so from here, what is the Y for shape 1? So Y shape 1 is measured from the centroid of the part 1 to the neutral axis. So that will be the Y1. Okay, so for this case, Y1 is equal to X over 2. And the area for part 1 is equal to 0.3 times X. Alright, and then plus, okay, plus Y2. Okay, so Y2 is the centroid, is measured from the centroid of the part 2 to the neutral axis. So that's the distance for Y2. Okay, so because Y1 and Y2 is in opposite direction, so we have minus here. Okay, we have minus. Okay, minus, minus. Okay, so Y2 is equal to 0.1 minus X. Okay, minus X. And the area for part 2 is equal to NAS, which is equal to 3.217 times 10 minus 3. Okay, so this one equal to 0. Alright, so if we expand this equation, we will have 0.15 x power of 2 minus, plus 3.217 times 10 minus 3x minus 3.217 times 10 minus 4 equal to 0. So using calculator, okay, using calculator, we get X is equal to 0.0368 meter or 36.8 millimeter. Alright. Alright, so now we know that the X is equal to 0.0368 meter or 36.8 millimeter. Okay, so now we can proceed to determine the I. So now determine I, moment of inertia. So the moment of inertia, the total moment of inertia is equal to the moment of inertia of part 1 plus moment of inertia of part 2. Okay, so if I expand this equation, so the I total basically is equal to 1 over 12 BH power of 3 plus A D power of 2 for part 1 plus 1 over 12 bh power of 3 plus a d square power of for part 2. Okay, so now the I total, okay, is equal to 1 over 12. So b for part 1 is 0.3, okay, 0.3, and h for part 1 is equal to x, okay, so which is equal to 0.0, okay, 368, okay, so power of 3, okay, so that is the h for this case, the h is equal to x, okay, for part 1, and then plus the area 0.3 times 0.0368, okay, and then d2, okay, d2 is for this case is equal to y1, okay, for this case equal to y1, okay, so from the centroid to the centroid, so for this case is equal to x over 2, which is 0.0368 over 2 square. Alright, and then plus the moment of inertia for part 2, okay, part 2, so which is 1 over 12 bh power of 3. So from here for part 2, okay, so this is the part 1 of shape 1, this is part 2 of shape 2, okay, so for shape 2, okay, for shape 2, you can see here the h, okay, the h is small, okay, the h is small, okay, this is small, which is approximately equal to the diameter of the steel rod, okay, the diameter of the steel rod, okay, approximately equal to the diameter of steel rod. So if the h is too small, okay, if the h is too small and then power of 3, so what happened? So h small value power of 3, so it's become a small value, okay, and then small value multiplied by some value here, so the value will be almost become very small, okay, so that we can cancel out this one, we assume equal to 0, okay, so again h is very small, and then the small value power of 3 is become small value, very small value, so and then multiply with some value here, so the overall equation here become the value for this operation become very small, so we can assume, we can ignore that value, okay, and then plus AD square, so A is equal to NAS, which is equal to NAS, we already calculate from the previous slide, which is equal to 3.217 times 10 minus 3, and then so D is equal to, okay, D square is equal to 0.1 minus S, okay, minus S square, okay, where the S equal to 0.0368, okay. Alright, and then we can solving this equation, this equation, so we get the I is equal to 1.783 times 10 minus 5 meter power 4. Okay, so now we have the value of I, so we can calculate the stress maximum in the concrete, which is equal to MC over I. So M is given from the equation, so is equal to 4.5 exponent 3 multiplied by C. C is measured from the neutral axis to the top surface of the concrete, which is equal to S. So S equal to 0.0368, and then divided by 1.783 times 10 minus 5. So this one equal to 9.287 megapascal. Okay. So for concrete, sigma max, okay, for concrete, okay, sorry, this is for concrete, okay, and sigma max for steel, okay, so I delete this one first. So for steel, okay, for steel is equal to the MC over I. Okay, so equal to, so N is 8, so transformation factor, so M is equal to 4.5 exponent 3, and then C, what is the C? Okay, so the C for the steel rod is measured from neutral axis to the what we call this one, to the rod, okay, steel rod. Okay, so multiply by, so I write here, okay, the distance from the neutral axis to the steel rod is equal to 0.1 minus 0.0368. Okay, and then divided by 1.783 times 10 minus 5, so we get equal to, okay, 127.61 megapascal. Alright, so that is the maximum value for stress in concrete, and that is the maximum value for the stress in steel. Okay. Okay, now let's proceed with example 5. Knowing that M, the bending moment M, is equal to 250 Newton meter, determine the maximum stress, okay, the maximum stress, which is the sigma max, in the beam shown when the radius of fillet R is equal to 4 mm. So that is the R. So this is the case that involve the stress concentration. So we have fillet here, okay, so this fillet basically induce the stress concentration, okay, the stress concentration at somewhere here, okay. Alright, so the sigma max basically is given by the K, stress concentration factor, multiplied by MC over I. Okay, so we need, from this equation, we need the value of K, and also we have to calculate the value of K and I in order to calculate the sigma maximum. Alright, so in order to calculate the K, so we need the value of the radius of the fillet over the diameter, the small diameter here. Okay, so that is a D. So basically this is the small d. And then we also need the capital D over D, which is, here is the capital D, okay, divided by small d here. Alright, so for our case, the R over D, okay, is equal to the 4 over 40. Okay, which is equal to 0.1, and D, capital D over D, is equal to 80 over 40, which is equal to 2. Okay, so using this value, we can calculate what is the value of K. Alright, so before that, let's calculate the value of I. Okay, so the I is given by 1 over 12 VH power of 3. So how I get this equation? So this is the I for this is the equation of I for rectangle cross section beam. Okay, so we consider this cross section. Okay, remember, so this is the cross section of the beam. Okay, so that will be the B, and here will be the H. Okay, So from here, so the I is equal to 1 over 12, so B equal to 0.008 and H is equal to 0.04, okay, power of 3. Okay, so from here the I is equal to 4.267, okay, times 10 minus 8 m power of 4. Okay, so now let's proceed to calculate the value of K. Alright, so we have the value of R over D, which is equal to 0.1, and capital D over D equal to 0.2. Equal to 2. So from this figure, R over D, which is here in x-axis, equal to 0.1. So means that this line, okay, this line. So that is the line for R over D equal to 0.1. And capital D over D is equal to 2. So this is the line for, okay, so this is the line for capital D over D equal to 2. Okay, see here. Okay, so we take the intercept point, okay, intercept point, and then we can calculate the value of K. So from here, the K is approximately equal to 1.9. I can say 1.8 something. Okay, let's choose 1.9. Alright, so now we can calculate the sigma mass, okay, in the beam, which is equal to K MC over I, and K equal to 1.9, so M equal to 250, okay, and then C, okay, so C, okay, alright, so this is the beam, okay, the beam, so here will be the sigma mass, sigma mass, so the neutral axis is somewhere here, so the C will be somewhere here, so that's the C. Okay, so from here, because the distance here is 0.04, so the C is equal to 0.04 divided by 2. Okay, and then divided by I, okay, the moment of inertia, which is equal to 4.267 times 10 minus 8. So sigma max from here, the sigma max is equal to 222.64 megapascal. Alright, so this is the value of sigma max, okay, based on our K, which is equal to 1.9. Okay, if we can get the exact value of the K here, so this value will be slightly different. Okay, slightly different. It's based on what's value we take from the graph. What's value of K we take from the graph. Alright, that's all. Thank you. Bye bye.